Thank you. Thank you for invitation and also for the introduction. I will try to persuade you that lightning-related processes occur at 10 orders of magnitude at spatial frequency and temporal scales. But before I do that, I will start with some introductory slides. What is lightning? What is the background for lightning initiation? How the signals generated by lightning discharges look like, to complement Andrei's talk from today, that you have more information and a better idea about what is happening before the Whistler wave arrives to the satellite. So, to start with, lightning is powerful natural electric discharge. We know it already from the time of Benjamin Franklin and his famous attempt with a kite. And there are about 2,000 active storms at the same time all over the globe, producing more than 50 discharges every second worldwide. And on the map, you can see the globe with lightning frequency, which is here represented by the color, and the color is the intensity of lightning per kilometer square and year. And you can see very nicely that the data collected by optical instruments on board NASA spacecraft show that lightning are more accumulated above the continents and in the middle and low latitudes. There is quite a few only lightning at high latitudes in both southern and northern hemisphere, and not too much around the oceans. There are some, of course, but the concentration is about the tropical continents. The reason why it is like that is one of the things which are clear to us, and it's the thundercloud itself. It looks like a huge tower, and it extends up to 18 kilometers in tropics, 12 kilometers in the mid-latitudes, and it's full of water and icy particles, which are called hydrometeors of different sizes. And such thundercloud has a much better condition to occur when there are larger differences in temperatures between night and day, which is around the continents, and if there is enough humidity, which is in the tropics. So there are nice thunderclouds. You can see here that they are somehow flat at the upper part, which is caused by the movement of the humid air with these hydrometeors up to the tropopause, which is the altitude when the temperature with altitude stopped decreasing and start to increase again. And then there the thundercloud cannot move and stop. Sometimes there is overshooting tops. If you see this, it's evidence of very severe weather because there might be tornado in it. So this is, not every thundercloud has such an overshooting top, so pronounced one as this one, but it's usually the evidence of very bad weather. These hydrometeors, which are inside the thunderclouds, are moving. They are falling down due to gravitational forces, and they are also pushed up due to the updrafts. And as some of them are already charged due to cosmic radiation and some due to radon coming from the Earth, some of them are charged already, and when they move up and down, they collide, and due to collision, they get more charge. And as the particles of different sizes, which you can hear, they are different from very small snowflakes and water droplets to hails, they get charged differently. The larger one get usually a negative charge, the smaller one get usually positive charge. So in the end, this is very simplified, but in the end, the more heavier are in the bottom, the lighter are at the upper part of the cloud, and the whole thundercloud serves as a huge battery. And if the electric field is strong enough, the discharge could be initiated. Is it simplified? Because there are not only 2 charge layers inside the cloud, it's much more complicated. There are at least 3. Another lower positive charge center at the bottom part of the Thunder cloud. There is a screening layer which is negative in the upper part of the cloud, and sometimes also at the different parts of the cloud, the composition of charges is different. The other problem which is with it connected is that the electric fields which were measured inside the cloud are 10 times lower than is the breakdown in the earth. So there needs to be another mechanism which allows the discharge to initiate. And there are 2 possibilities which were proposed by scientists. One is that the electrons which are coming from the universe, cosmic radiation, react with the atmospheres, produce secondary so-called runaway electrons, which are so energetic that they are very fast, and they collide with particles in the cloud, produce additional ionization, and this additional ionization effectively lowers the electric field, and then the discharge can be initiated. The other explanation is that the hydrometeors are simply not like balls, that they have sharp edges, and around these sharp edges there is locally increased electric field, and then the corona discharge can occur around these peaks in these icy particles, and this corona discharge starts at the beginning of lightning discharge. Maybe combination of both is needed to have a lightning initiated. We have different types of lightning. Here is the simple table showing how we can divide them. We have natural lightning I will be talking about. There are also man-made lightning, intentional, unintentional. Intentional are rockets triggered like that you simply send a rocket inside the cloud, and the discharge can be initiated, and you can then at the bottom measure, for example, the peak current which is flowing in the channel. These are unintentionally initiated from tall structures, because if there are also some peaks, this is the Eiffel Tower, but you can find on the internet other pictures with different chimneys and columns. Then the upward going lightning can be initiated. And in the natural lightning, we have cloud-to-ground lightning. It means lightning which goes from the cloud directly to the ground. These are only 10% of the whole family of the natural lightning. And then the cloud lightning, which are inside the cloud, so-called intra-cloud, or between different charge centers of neighboring clouds, which are intercloud, and these are 90% of it. And these cloud-to-ground could be also downward and upward. So I will show you later also the fast camera video showing one downward and one upward going cloud-to-ground lightning. If you look at this picture, here are these 3 main charge centers displayed. This is the main negative charge center. This is the upper positive charge center, and this is the lower positive charge center, which is usually quite weak. And here are the lightning cloud-to-ground, these 2. This is called positive because it's originating in the upper positive charge center. This is negative one, which originates between somewhere the negative and positive charge center in the lower thundercloud dipole. And even if you look at the sky during the next thunderstorm, which can occur in any day, you can distinguish between these 2, because this one is usually branched very heavily. The positive one is usually not branched at all. And these positive cloud-to-ground discharges form only 10% of all cloud-to-ground discharges. Negative ones represent 90% of all cloud-to-ground discharges. This is very interesting phenomena, these positive cloud-to-ground discharge, because as it is initiated in the part of the cloud which is a little bit extended, this is the candidate for so-called bolt of blue, because here this is at the tropopause somewhere 15 kilometers, and you might see nice blue sky above you, but there might be this end. And so this is the explanation for bolts from blue. Now, here you can see the development of this usual negative cloud-to-ground lightning strokes. This is the photo taken by a high-speed camera. I will show you the video in a while. And these are so-called leaders, which propagate towards the ground, nicely branching. Some of the branches extinct, and only one usually reaches the ground. So here at the time zero, we have thundercloud where there is enough charged particles, and the conditions are just prepared for the lightning initiation. The first phase is called preliminary breakdown or initial breakdown phase, something that happens. The corona discharge probably starts to occur inside the cloud, and then the lightning is looking for their way inside the cloud, ionizing the way until the moment when it reaches the bottom of the thundercloud, which might be around 2 kilometers above the ground, but it's very different at the different locations and different seasons. For example, in Japanese winter storms, this bottom of the thundercloud is only 50 meters above the ground. But usually, for example, here we would have like 2 kilometers. And now it propagates in steps, branching. Each step is approximately 50 meters long. And whenever it approaches the ground, where if there is some objects which is elevated, the upward going discharge can go against it. And when these two connect, then we have the lightning which you know. So it is the lightning which we hear, which we see. And the fully ionized channel is here created. It has about 10 centimeters in diameter, 30,000 degrees Celsius temperature, very hot, fully ionized channel. And the current which is flowing there for less than 1 millisecond usually can reaches on average 30 kiloamps, but we have evidence that there are also lightning strokes with the peak current of several hundreds of kiloamperes. If there is still enough charge in the cloud, then the current can continue to flow, quite low current, tens to hundreds of amps. And then another lightning source could be initiated, and it could follow the same channel, or it can form another channel or partly follow the channel. I will show you a few examples. And this additional discharge is called subsequent return stroke, and it happens usually from like 5 milliseconds up to several hundreds of milliseconds after the first one. And we can have in a row more than 2, which I'm showing here. One of the documented records was about 30 strokes in the same channel or in the same time window and place. The positive ones usually do not have any subsequent stroke or only one. I am usually using the thunder to wake up the students, but I hope I will not need it here. I hope you will enjoy my talk. So you can interrupt me whenever you want to ask something. Don't be scared. Here it is negative cloud-to-ground lightning. You can see that sometimes the next discharge follows the same channel. Sometimes it simply follows only part of the way. Sometimes it extinct. So it's interesting high-speed video, 7,000 frames per second. I think I need to. Does it go? Yeah. So here you can see some chimneys, and there is lightning, upward lightning generated in one of these chimneys. And these are usually spreading in such a funnel. And if you don't see the lightning channel all the time, only partly. It's not because if it doesn't exist and there are some isolated parts, it's simply not visible because the current is so low that the luminosity is not captured by the camera. So very nice results came using these high-speed cameras, but because you now can clearly see how the discharge evolves and which part is connected to the ground and which part extinct. When lightning propagates inside the cloud, it also propagates in steps. And in every step, a radio burst is generated. And if you have an array of antennas, as here is the low frequency array antenna, which is dedicated for radio astronomy, but the colleagues found that they might nicely follow the propagation of the lightning discharge inside the cloud. This is a huge discharge which was spreading in the Dutch thundercloud, which are usually quite extended. And this discharge didn't reach the ground at all. But this distance could be easily 50 kilometers or even more. The candidate for the largest or longest discharge reached nearly 800 kilometers. It was seen not by such an array because it would be not possible, but using the geostationary lightning imager, the optical one, when they see the whole Northern American Great Plain and the discharge were crossing 3 states, 800 kilometers. So the radio signals are very nice to look at the propagation inside the cloud, where it is optically not so easy because usually the cloud is not transparent enough to see these small currents which are flowing in the cloud channels. The way how the localization is made is very simple. I think this is the only equation which I will be showing. Yeah, and this is very simple because if you have more than 3 stations, you can, and you know that the lightning signal is propagating by the speed of light. So it's finite speed. So, and every station detected the burst of the wave packet at a slightly different time, and you put it in the set of equations for every station 1. You can then calculate the location and the time of that radio burst. And the same system is used when you calculate the 2D positions in case of lightning location networks, which are the commercial ones. So I can now show you how it looks like if you do such calculations. You can have these nice plots showing the propagation of the discharge within 3 dimensions and time. Here it is color-coded by the time, high time flows. This is altitude. And if you look at the altitude and the one of the horizontal components, you can see that here it's probably the positive charge region, here is the negative charge region, and here lightning in between. Lightning is initiated. Here you can see how it starts propagate upward. There is another branch going upward, some small ones nearly vertical, and the discharge is quite complicated. And this one here is 16 kilometers and is something similar. Based on the energy of individual radiated sources, you can guess if it is the positive or negatively charged part of the cloud, because in the positive charge, usually the radiation is much weaker. So here it's estimated how it looked like. So this is the lower negative charge center and the upper positive charge center, and the majority of intra-cloud lightning discharges look exactly like that. initiation somewhere in between, and then so-called bidirectional propagation in the opposite charge regions. You saw already this picture. This is how the signal propagates in the so-called Earth ionosphere waveguide, which is like 70 kilometers wide during the day and about 90 during the night. And if the signal, if the lightning produces the signal at a huge range of frequencies from hertz up to gigahertz, part of it can easily propagate in the waveguide. It is this kilohertz range, so-called very low frequency range. And it can, here is a discharge, it can propagate as a ground wave. It means around the surface of the Earth. And for longer distances, it's reflected from the ionosphere. During the day, the reflection is quite bad because the signal is attenuated. There is at 60 kilometers too much neutrals and the attenuation is huge. But during the night, ionosphere, it could be reflected many times, and you can have the signal propagating for more than 2,000 of kilometers in the waveguide. And you can also, based on the properties of the signal, guess what is the height of the ionosphere, because there is a critical frequency of the waveguide, and it can be seen on the spectrograms showing these signals, which are called atmospherics or shortly spherics. And these signals are used by lightning location networks. As you can see the map here, this is the Euclid European Lightning Detection Network, and this is 1 year of data, 2014, and we are now in January, and you can see that in January the continent is simply too cold to produce a nice thundercloud, and the majority of lightning is accumulated in the Mediterranean Sea and in the Atlantic coast. And when we go more to the summer, then lightning move more to the continent. The negative strokes are simply dots or small squares, and the positive ones are crosses. So you can see that even in winter you can have lightning in Norway. This is from the fronts coming from the Atlantic Sea. There is sometimes nice hotter air, which then, when it arrives to the coast, then thunderclouds could be initiated. Such winter lightning is usually quite strong and not very frequent. So now we are in April, and you can see that we start to see lightning around above the continent. Usually all the fronts came from the Atlantic Ocean, but sometimes there are also other movements of the clouds from south to the north, or even from the east to the west. And Euclid has about 150 sensors all over Europe. This is the one which is the most frequent one, and they have a quite nice detection efficiency, 95% of cloud-to-ground strokes. Of course, it depends on the peak current, because the signal which is generated by lightning is dependent on the current. Yeah, it's a changing current produces magnetic field, and the changing magnetic field produces changing electric field, and electromagnetic waves can propagate for quite long distances. This is also quite nice precision for, of course, for cloud-to-ground lightning, because in case of intra-cloud lightning, if it covers 30 kilometers, you have no idea where it happens, and you cannot define it by one point. But they use simply the exactly same procedure, because they do not have other possibility how to estimate how the intra-cloud lightning is behaving. And now we are in September, and still there is quite a lot of lightning in Southern Europe. And if we go towards the winter again, the picture will again change, and only the oceans are able to produce a thundercloud with lightning. We can see lightning also from space. The left figure shows the lightning detected by the geostationary lightning mapper on ghost. These are oysters. Yeah, you heard them already, not these ones, but the other ones. I forgot that I didn't need to click on it. So every yellow dot is one lightning flash detected by this geostationary lightning mapper. It has 2 millisecond frame rate and very nice, huge CCD imager with a spatial resolution of 8 kilometers. And this is the infrared figure of Hurricane Harvey. This is the hurricane which hit the US coast in 2017. And you can see that there are even lightning in the eye of the hurricane, but the majority of lightning was concentrated in these rain bands. And it was not quite clear before that hurricanes are electrified and produce lightning, because you would not expect it. What I was speaking about, there are hydrometers moving up and down and creating by gravitational forces the charge layers, but the hurricane is simply rotating like that. But there are overshooting tops in these rain bands. And in these overshooting tops, the official charging can happen and lightning can be initiated. So you know now from Ondřej's talk, I will not spend time on it, how the whistling sound is formed, that simply the different frequencies arrive at the different times to the receiver. And here it's time frequency spectrogram showing a few of these Hurricane Harvey lightning detected at the orbit around the Earth by Van Allen probes by the emphasis instrument. These are very short. The delay between the frequencies is quite small. It means that the spacecraft was quite close to the discharge, and the discharge didn't propagate it a long way through the plasma medium. So this is an overview. This was an overview how the lightning-related signals can look like. And here now I will be showing these time scales on a few examples. So in the temporal case, we can see signals which here this plot shows nice pulses which are produced by the propagation of the leader inside the cloud when the channel is slightly ionized still. So it needs only a little bit to ionize it more to that the current can flow. And such pulses are detected by electromagnetic receiver. This is the magnetic field receiver we placed in Netherlands to be able to cooperate with this low frequency array. And here is the signal from this low frequency array with localized sources of the radiation at around 7.8 kilometers. And these rising and falling edges are very fast. And so here we have like nanoseconds length of these rising edges. Here, do you know what it is? What it could be? It's probably lightning, no? Because I promised to speak about lightning all the time. Here is the so-called Whistler echo trains. If you have lightning, it generates a signal which propagates through the ionosphere, and it follows the magnetic field line to the other hemisphere. You heard about it. But it can reflect if there is some guiding plasma irregularity, so-called duct along the feed line. It can reflect and go back. to the northern hemisphere, and it can back again. And every time it produces at the receiver one whistler. And the delay between the frequencies, so-called dispersion, is accumulated because the signal goes back and forth for many times. And here, it's nearly 4 seconds when the lightning-generated signal was bouncing in the magnetosphere. So here we have minutes. These are another examples. These vertical lines are these so-called atmospheric or spherics from the original lightning strokes. So this is the original signal, and these are these individual bounces in the magnetosphere. And we can have also longer phenomena. For example, if we have so strong lightning strokes as we saw here in this study, more than 100 kiloamps, it can influence the bottom of the ionosphere and make some disturbances. And it took about 20 minutes before such disturbances disappear. So we have now here examples of nanoseconds to 20 minutes, 10 orders of magnitude. In the frequency range, we can have on the upper part of frequencies lightning-generated signal at the gigahertz range. This is so-called narrow bipolar event, which is a strange intracloud lightning. Nobody up to now knows how it is initiated because it appears without any initiating processes. And it's very narrow and very energetic because it radiates in high frequency part of the spectrum. It's the strongest natural radiator at tens of megahertz range. And this is the signal detected by broadband receiver with a frequency band ending by 10 megahertz. Here are the points which came from the interferometric measurements by several stations. And here it's the narrowband measurement around the 1 gigahertz range. This plot shows also the high frequency part of the spectra. There is a radio frequency sensor at the geostationary orbit, and it can detect these narrow bipolar events. And you can see it here. We have here but 2 traces because this narrow bipolar event, very strong and narrow radio pulse, is produced inside the cloud. So the first path came from the direct propagation of the discharge to the geostationary orbit. The second one just goes to the Earth and reflects it and goes to the satellite again. So from the delay, which is here in microseconds, it's about 60 microseconds. You can calculate the altitude. It's simply geometry. Altitude of the at which in the thundercloud this discharge was generated. Here is the low frequency edge. This is taken from Ondřej's paper, 2023, and you can see the lightning whistler, and it's kilohertz range. Yeah, the path here, the trace is not very narrow, so it means that in this case the signal was propagating several paths. Yeah, it was not a single path. It was not ducted. It was propagating so-called unducted. So then the signal penetrates the ionosphere at different places. Then it propagates in the magnetosphere and arrives to the satellite at different types. Here, this lightning whistler seems to be generating or triggering the plasmaspheric His emission you also heard about. Here we are at the low frequency edge. I'm not sure you might hear about the Schumann resonances, which are the constructive interference waves, standing waves coming from all discharges which are around the globe. And in the cavity between the Earth and the bottom part of the ionosphere, there form standing waves. The basic frequency is 8 kilohertz. You can easily calculate it from the diameter of the Earth and from the height of the ionosphere. And then there are higher harmonics of these 8 hertz. And you can see them all the time, but sometimes they are, the intensity is increased. And this is an amazing event. You might remember at the Hunga Tonga volcano eruption. It produces so huge amount of lightning that on the global scale, it was measured as an enhancement of Schumann resonances. This is just 1.5 hours of this intense part. No, I don't want this. I cannot, I'm sorry, I will not touch the screen. Yeah.
I don't know.
I can probably not, no, yeah. So, is this here or?
Yeah.
No.
Yeah. There we go.
Okay, so I will not touch it. And the amount of lightning strokes produced during that volcano eruption was so huge that all the lightning detection network, the global ones, were saturated by these emissions and had lower efficiency in the other part of the world. So you can see nice pictures about how the lightning discharges were spreading in circles from the volcano to all directions. So this is the lower part of the frequency spectrum. And here, as regards the spatial scales, I told you that we have the composition of hydrometeors inside the cloud. And these figures these are real figures taken using a camera on a plane, and nice different shapes. And so they have these cloud droplets, the small ones, 2 to 50 micrometers, and the ice crystals and larger crystals can have sizes up to 10 millimeters. And at the scale of the larger distances, this is the paper I was mentioning to some of them, yeah, some of you. This is from the Alexandra Watt et al. Paper. She was looking at the whistlers detected by Van Allen probes at different Earth radii. You can see that the lightning whistlers appears also around at the distance of about 6 Earth radii. So we have here again 10 orders of magnitude in spatial scale. To these large-scale phenomena, which are produced by lightning, are so-called transient luminous events. Does somebody of you heard about it already? Yeah, you did? These are optical phenomena which are related to underlying, usually positive cloud-to-ground lightning. Not all of them, but one of the most frequent ones is so-called sprite. It should resemble something like a dwarf with the hair hanging. Yeah, you need to to have a lot of imagination to see it in it. Yeah, sometimes it looks like a carrot. Yeah, with the roots. Simply, this is a sprite. These are a family of jets. Blue starter, blue jet, and gigantic jet, which has nice 2 colors, which are related to the color which is emitted by molecular nitrogen, because in higher pressure it emits blue color. In low pressure, pressure is decreasing with altitude, it emits nice red color. This is very recent one. It was discovered in 2019, GHOST, and you can see here green emission from oxygen in sprite tops. It is the same color which you saw in the aurora videos. So it's atomic oxygen radiation. And here this huge one is called ELF, which is emission of light and very low frequency perturbations due to electromagnetic pulse source. It is a donut shaped, here is a hole, and in the middle of the hole is the causative discharge. So if we have very strong discharge, you can imagine that its lightning channel acts as an antenna. I know, I showed that it's very complicated, but if we think it's simply wire, only dipole, his diagram, how it's radiated, it looks like that. So just in the middle, it's not radiating anything. That's why it's here a hole. This is very fast phenomena. It spreads up to 400 kilometers laterally in 100 microseconds. So you cannot see this by naked eye. But you can see sprites, because I will show you that the evolution of sprites is not so fast, and you can see it. So how you can see it? You will look at the radar data. You will be in the nice weather. In the radar data, you find a distant storm, ideally the mesoscale system, large one. You look about like 200 kilometers, 300, even 500 kilometers from your place, and you have to be in nice weather to be able to look above that distant storm. Yeah, and then you will try to have the eyes open all the time. Yeah. So these are a few examples of nice sprites, and this is the ELF. And this is then evidence that even the astronomers like it, because every day NASA releases the astronomical picture of the day, and sometimes there are also lightning events like here. So it's very nicely visible, the streamers of sprites in high resolution. These sprites are called columniferous sprites because it doesn't resemble any carrot. And here is a huge ELF. This slide shows the evolution of a sprite. At the time t equal to 0, there was a positive lightning stroke. Here you can see this is not the cloud. This is the bottom of the ionosphere. Yeah, you can see it here in the altitude. Here is 80 kilometers. This is a huge event. It spreads around like 30 kilometers in altitude. Here was probably an irregularity at the bottom part of the ionosphere, where the intense electric field, which occurs between the upper part of the cloud and the bottom of the ionosphere after the strong positive discharge, initiates the beginning of the sprite discharge, and it propagates simply down. And here it's like fully developed. It's a discharge in the not fully discharged in the weak pressure, and then it died out in 10 milliseconds. This is something which the naked eye can see. It didn't happen to me. I was not I had not lucky enough to see the sprites by my own eyes. Here is the picture showing how it's big if you compare it with Jupiter, for example.
Is it happening very often, or is there specific conditions?
It's, in fact, it's not very clear how often it is happening, because you need to have cameras directed above the thunderclouds. The electromagnetic evidence of sprites, it's not so clear. So there are some models showing that you need to have some conditions which the causative lightning discharge needs to fulfill to create such transient luminous phenomena. For example, for ELFs, it's clear that the peak current needs to be huge to radiate so strong wave that it can ionize the molecules at the bottom of nitrogen at the bottom of the ionosphere. In the case of sprites, there is another property of the lightning which needs to be fulfilled, and it's a so-called charge moment change. This is the amount of charge which is transported in the lighting channel. This is the reason why the positive lighting, or the majority of sprites, is caused by positive lighting, because the lighting channel is simply larger. So there's more kilometers when the charge is transported. And it looks like that there needs to be also some continuing current phase. And if you combine everything in a model, it looks like that around 200 Coulomb kilometers are needed for a sprite to be initiated, but it's still not enough, because it looks like that some irregularity in the ionosphere needs to be present as well at the same time. Yeah. So from the satellite measurement, there was a mission for Taiwanese called Formosat, and they didn't go to higher latitudes than I think for 35 degrees or 40 degrees north and south. And from their measurement, optical one looked like that there is they have in their collection the largest amount formed elves, not sprites. But the different amateurs who are trying to catch transient luminous events, they usually are recording sprites, not elves, because elves are usually not very bright and are also quite short. So the sprites are the most, I think, the most recorded ones by amateurs. This is the gigantic jet. This is originating directly inside inside the cloud, and it has these two colors. And here it's this ghost. It was funny because at the beginning the scientists who operated the camera saw, okay, I had something on the objectives. It's something not natural. Whenever there's something strange in the objective occurs at 3 places around the Earth, then they started to think it might be real, and it was found, and it was already modeled, that this is this green emission coming from atomic oxygen. And you can see here the wavelength, and here it's nitrogen lines in high pressure, nitrogen lines in low pressure. This is the molecule of oxygen, which is also in the red auroras. And here is the atomic oxygen line. Here I'm showing quite a recent paper. The colleagues from Spain, I think they detected about the mesoscale convective system in Colombia, several gigantic jets. You can see them here. And they were able to use this array of antenna to look how it looked like if you detect the radio sources. And you can see here with the colors there is a reflectivity of the cloud, and it's coming out of the cloud, and the radio sources were detected up to 4 kilometers altitude. And this figure shows nicely, this is the 30 dB reflectivity, that there was this strange hill in the reflectivity from which the gigantic jet was initiated, and this is the top of the cloud, and here is the upper positive charge coming out of the inside the cloud, and here also above the cloud. So these gigantic jets are not very often, and what are the conditions for their initiation is still not fully known. I was talking about these narrow bipolar events, and they were found to produce blue light. So it was quite recently where it was found that these blue jets are related to narrow bipolar events. You can see here the detections of from the photometers which are placed on the atmosphere-space interaction monitor on the International Space Station. And this is the blue line is the photometer at 3C7 nanometers, and the red line is on 777 nanometers. And it's a nice enhancement of the blue emission, and in combination with ground-based detection of narrow bipolar event, it was quite clear, and they accumulated more data, that blue jets are simply related to these mysterious intra-cloud emissions. This is another example, but a little bit later paper, the same instrument on board the ESS, blue emission, nearly nothing in the 77 red one, which means that the lightning channel is probably not hot, because if it is hot from the return stroke, we see red emission. But here we see nearly only blue emission. It means that the narrow bipolar event is a system of streamers. And here is the projection of the asim trajectory, and here is the storm. And using the radio data and the ionospheric reflections, you can calculate the altitude of the distance, and it came out that they are both polarities of narrow bipolar events. These are negative ones and positive ones. The negative ones extending above the stratosphere, and the positive ones which are happening in the upper part of the thundercloud. This is the overshooting top here. And it's also clear here that the signal from the blue signal from the negative one, which is happening at higher altitudes, is not so scattered by the cloud as the positive one, which is more influenced by the cloud thickness, and is also not so intense. So we still do not know how these narrow bipolar events are initiated inside the cloud, but we at least know that they are emitting blue color. This is also interesting picture, a recent paper. Try to measure the ghost spectrum. Again, it was quite strong, quite huge mesoscale convective system. After the positive cloud-to-ground lightning with a peak current of nearly 200 kiloamps, the ghost was detected, and here is the spectra. These are different wavelengths, and here you can see what you would expect, yeah? Oxygen and nitrogen, but here you have also iron and silicon. So as a conclusion of this paper was that the spectra of ghost reminds quite nicely the direct measurements of meteoric metals in the mesosphere and lower thermosphere. So it is possible that we need to have thunderstorm and meteorite at the same time and high electric field to initiate a ghost and have this nice green emission. Have you ever heard about terrestrial gamma ray flashes? This is another phenomena which is related to, it's not optical, related to thunderstorms. Terrestrial gamma ray flashes are short flashes of high energy photons, which were detected mainly by satellites. And gamma glows are enhancement of the background radiation in thunderstorms detected on balloons, planes, or on the high altitude observatories. And they were discovered by satellites which were dedicated to measure the gamma rays coming from the space. And then they were quite surprised when they detected gamma rays coming from below, from the thunderstorm areas. But it was not clear if, again, every lightning can generate gamma rays, or if it is only a special type of lightning, or if it needs to be strong, or how simply the normal lightning generating terrestrial gamma flashes looks like. This was changed in 2023 during the AGU conference. They presented the first results from the Aloft mission. It was the brave pilot who was flying just above the thundercloud tops in a Mexican Bay. And the plane was equipped with a huge gamma ray detector with a measurement of the electrostatic electric field. There was a radio receiver and camera, and it came out that the glows, gamma glows, is so dynamic that nobody knows before about it. That they presented it, there's a thundercloud from above, it's a boiling pot where simply the gamma rays are coming from all parts. And probably, or it's quite sure based on the models, that this is Bremsstrahlung, which is generated when the electrons are propagating inside a very strong electric fields in the upper part of the cloud. And they, when they are then slowed down, they emit Bremsstrahlung. And so, before, we just simply saw that the gamma glows look like that. And with better instrumentation and to be much closer to the thundercloud, it looks like this is more dynamic. Even more mysterious is this measurement. This is so-called flickering gamma ray flash. This is the measurement of gamma ray emission in black line, and this orange or whatever it is, red one, is the electric field. And you can see that here is nothing detected in the radio during that burst of very regular gamma flashes. So it's still completely mysterious, because we thought that we needed to have something like intracloud discharge with a current to produce the gamma ray flash. But so it's not clear if simply this is so low in intensity in the radio signal that it couldn't be detected on the, I'm not sure now if this was on the receiver or, no, I think it was from ground measurement. And here is the mysterious narrow bipolar event, which starts the pulses in the radio emission. But why this flickering gamma ray emission is so silent in radio, it is a complete mystery, and it was not answered up to now. So I didn't expect, after so many years of investigations in lightning topics, that something can come so surprising result, which nobody expected. So now there are plans to have the Aloft 2 to go at other places, and then to have much better radio receiver on the plane to look if this is really silent or if it is detected from ground. Here I'm showing the results detected on the International Space Station. It is here at the same time. This is ELF and gamma ray flash, which was caused by an intracloud lightning propagating between the main negative and the upper positive charge layer. It was so strong that it was able to generate ELF, and it was able also to generate gamma ray flashes. It was published in Science, so this is the artistic expression of what was happening. And there are more events like that. Here are they displayed by the different shapes and different colors, all of them happening around the equator. And for this study, the authors used two global lightning detection networks. One is so-called WLAN, Worldwide Lightning Location Network, and the other one is GLT 360, operated by Vaisala. They have around 70 sensors, each of them. Vaisala is able to estimate the peak current from the strength of the magnetic field or electric field pulse. And you can see that in the majority of events, these intra-cloud lightning were super strong. This is even strong for normal cloud-to-ground lightning, and intra-cloud lightning are usually much weaker. But these are like huge numbers. Yeah, intra-cloud lightning reaching nearly 500 kiloamps. It is not clear how this can happen. So there are still quite a lot of things which we do not understand, and the investigation needs to continue. So this is the part which is related to the ground, to the terrestrial lightning. Now I will switch to the planets, but maybe if you have some questions to what I already said, you can ask now. Go ahead.
Why is we have almost only detected in the ocean, because you said the ocean was maybe in summer.
Yeah, it's true. It's true. It doesn't mean that there are no lightning events above the ocean, only that there are not so many as above the continents. And there are also discussions if this discrepancy is based on the detection efficiency of lightning detection network, because simply the signal needs to, in the middle of the ocean, the signal needs to propagate quite a long distance to the nearest station. But from the optical data from the space, it's quite clear that it's not the case of the detection efficiency. Yeah, but in this case, probably there were these huge mesoscale convective systems which are maybe in this case produced above the oceans. In fact, I do not know. I do not know. Yeah. The ASIM is measuring between plus 50 and minus 50. So it should be there. If it is happening at other altitudes, they might be able to detect it. So, but they didn't. So I'm not sure why these super strong intra-cloud events are happening above the oceans mainly.
I was going to ask about Q-bursts, because you hadn't mentioned them, but we run 2 induction coils in Scotland, and about every 2 or 3 minutes you see an enormous spike in the EM energy. Someone told me they were Q-bursts.
Q-bursts, yeah. This is something, different. This is the Q-burst is a very transient signal which is superposed on Schumann resonance signal, and it's related to one stroke only. So it's if you have something like that, several hundreds of kiloamps, it can produce like spike in the Schumann resonance signal, and this is called Q-burst.
Okay, but it's not a particular kind of lightning, it's just a particularly large one.
It's not optical. No. It's like electromagnetic phenomena.
It's just standard.
Yeah.
I have a question.
Yeah.
Okay, I think from the first or second slide that you showed, the lightning frequency.
Which slide?
I guess the second where you showed the distribution of the lightning. I think the first or the second slide or so. Yes. So, I mean, it appears we have more lightning in Central Africa, if I'm right.
Yeah.
So I'm curious to know why maybe I think we have Congo there or something, could be the rainforest or something.
There's probably here, it's really humid area. I think that it came from the humidity in this case. Humid and warm and hot, high temperatures. And in the night, during the night, there might be lower temperatures, so the difference between the night and day temperatures and the huge humidity can lift up the humid air to the altitudes when some of the particles are frozen, and then the effective charging can happen.
Yeah, but I'm curious to know because in the South American region, which is the Amazonian region,
It's
the climate is pretty similar.
It's true. There is a lake which is called Maracaibo in Venezuela, where is the largest amount of flashes at all. There is storm 300 days a year, and nobody understands why it's like that, because maybe it's there is partly salty water, and the salt is considered, if it is lifted up, to serve as condensation nuclei. So maybe that salt, which is because the lake is opened to the sea, causes something like that. It's also known that the condensation nuclei can come from the pollution. So if you look, for example, at South America, big cities, you can see more lightning during the work days than during the weekend, because the big factories are closed and there is not as much pollution as during the work days. In Northern America, it's the opposite, because the climatization, the air conditioning is probably in more places at homes switched on during the weekend, not during the working days, and the pollution in North America is probably not so huge, yeah, than in South America. There is also a study showing how lightning behaved during the COVID times. It was shown that in Italy, where the closures were really huge, they closed nearly everything with less lightning, because the pollution is not so huge, and simply there is a smaller amount of condensation nuclei and smaller amount of lightning. So here in these most intense areas, this is also in Indonesia, are close to 70 lightning per kilometer square, and here. In Europe, we have about 2 lightning per kilometer square a year. From this distribution is also quite clear why we are not able to harvest the energy of lightning, because if you have 2 lightning per kilometer square in a year, how you will do that? Yeah. There were some attempts even if at the 17th century, but not successful up to now. Yeah. Because the energy of 1 lightning stroke is huge. It's gigajoules in 1 single stroke, but also a very short time period, 100 microseconds, but still. Yeah. We calculated with Ondřej for some TV emission about science that the 1 single lightning stroke can supply the electricity for 1 village to switch on the lightning, the lights on the streets for half a year. So if we are able to harvest energy from lightning, we would be happy. We would not need the oil. So can I move to planetary lightning? Or do we do the break? Or I can finish the planetary lightning, and then between the practical part we can have a break, or it's up to you. Yeah? Yeah, okay, so I will go through the planetary lightning. You know, these are whistle traces. These were detected by Voyager. Scientists didn't have any other explanation for their presence in the spectrograms, that there is lightning on Jupiter. So it was the first evidence of lightning outside the Earth. It was in Jupiter. Jupiter has atmosphere. It has water clouds. It has similar lightning as we have on the Earth. There is also lightning on Saturn. These Saturn lightning were detected as Saturn electrostatic discharges. Yeah, you can ask, yeah. Okay. Saturn electrostatic discharges. This figure is based on Cassini data, but they were also discovered by Voyager. And here you can see the huge storm. It was the largest storm in the solar system. This is only a few hours, but that storm lasted for more than 100 days. There are also some lightning whistlers detected by Cassini around Saturn, and it is surprising that we still don't know why there are so few of them, because on Jupiter there were many. I was probably wrong in saying that Voyager detected lightning on Saturn. Andre, can you help me? Was lightning on Saturn detected by Voyager? Not. I'm not sure. This figure is from Cassini, but
Voyager saw lightning in Saturn.
and Saturn as well.
Not as this one, but
Yeah, Saturn. I showed that before. Yeah, yeah, it's true. Okay. So, thank you. So these are evidence that there are lightning or the other two giant planets. Uranian electrostatic discharges detected during the Voyager 2 flyby, and whistlers, these traces, detected close to Neptune during the Voyager 2 flyby. Only 16 whistle-like events like that. Here you can see that the dispersion is really huge. Yeah? The delay between these two ends of the whistler is nearly 40 seconds. So the scientists cannot invent any plasma medium which will create such a dispersion. So they came with this theory that here was the lightning source and the signal was traveling between hemispheres and moving in latitudes to reach Voyager. We do not know too much about lightning on gas planets except of Jupiter, because there is a Juno spacecraft. This is the NASA spacecraft which is orbiting around Jupiter from 2016, and it is coming very close to Jupiter. Voyager was, I think, at the closest approach around 6 Jovian radii, but Juno is coming down to 1.1 Jovian radii, so very close to the Jovian surface. And it has 3 instruments which are able to detect electromagnetic signals from lightning. One is the low-frequency receiver. Here you can see again the whistler, but very low dispersion, a few milliseconds only, because it was detected very close to the planet. And we call them rapid whistlers because in comparison with these several seconds long signals detected by Voyager, they are really, really short. And if you look, when was Juno at the time it detected lightning whistler and propagated the signal along the magnetic field line to the surface of Jupiter and put the cross everywhere when Juno saw the whistlers, you come up with such map. And it's a little bit different, not from what we have on the Earth. On the Earth, which we are discussing, just lightning are accumulated in tropics. But here, there is in the tropics nothing, nearly. Yeah? The explanation is that on the Earth, we have the most energy coming from the sun, which is in the equatorial region. In case of Jupiter, which is more far away from the sun than Earth, then it's not enough energy from the sun. So the energy for lightning or for forming of thunderclouds, the heat is coming from inside the planet, and it's releasing in the mid latitudes. And there is another process which is going on Jupiter. There is quite a lot of ammoniac in the equatorial region of Jupiter, and the ammoniac serves as an active antifreezer, which prohibits the formation of proper composition of icy and cloud particles to have the effective charging and to initiate the lightning discharge. The other instrument which is measuring also in the electromagnetic region is the high-frequency part of the low-frequency receiver. Here is the new signal which was discovered by Juno, so-called Jupiter disperse pulse. Again, it's a signal which propagates, and the frequency of the signal approaches some level for which it cannot propagate. The distribution of these signals projected on the map again shows the majority of lightning in the middle and high latitude regions. And the last instrument which was able to detect lightning is the microwave radiometer. It was for the first time where in the 60 megahertz range and 1.2 gigahertz range lightning was detected outside the Earth, and each circle is one lightning detection. Again, it's very similar with some exceptions that the lightning related signals are accumulated in middle and higher latitudes. Here is the figure which shows the detection of lightning whistlers from the whole nominal part of the mission, and the color shows the number of whistlers per second in the logarithmic scale, and it's the same as the previous figure, which shows only the quarter of the nominal mission. Simply the lightning occurs only in mid-latitudes and higher latitudes. Here I'm showing an example of long dispersion whistler, the same as was detected by Voyager. These are these signals. If you look at the projection of the trajectory of Juno, these long dispersion whistlers were detected when Juno crossed the Io Taurus. And this is the explanation for the dispersion, for the large dispersion. It was also presented during the Voyager era, that when signal propagates through the dense Io Taurus, plasma Io Taurus, then it accumulates the dispersion, which is larger, and can be then even a few seconds. So it was the same signal as detected by Voyager. We also did a study on high resolution data, where we were able to detect like groups of pulses in the high frequency part as a multiple Jupiter dispersed pulses, but also as multiple whistlers, which you can see here. And it was for the first time when the radio receiver with such nice time resolution was orbiting the Jupiter. And we came out with the explanation then this might be an evidence of the stepwise prolongation of lightning channel on Jupiter, a similar one as we have on the Earth. Because the interpulse interval, the medium, was around 1 millisecond. So based on the analogy with terrestrial lightning, we thought, what are the repetitive signals in terrestrial lightning? Here, this is the millisecond scale. Here are first lightning stroke and the subsequent stroke going in the same channel or partly. But this is probably too long, taking into account that Jupiter is a much larger planet. Here are the pulses, which are so-called initial breakdown pulses, which are related to the propagation of the signal inside the cloud after its initiation. This is now nearly 2 milliseconds. And then these are the less regular pulses with larger distances between them. And these are propagating at the beginning of intracloud discharge. So based on this analogy, we assumed that what we saw on Jupiter might be the stepwise prolongation of intracloud lightning on Jupiter, because there is probably no cloud-to-ground lightning, yes, because there is no ground on Jupiter. So there are probably only intracloud lightning. There are also elves on Jupiter. This is this one. This is the figure showing the UV measurements made by Juno. This is the UV coming from the aurora, and there is no other explanation for such a emission, which is very small and in space, that it might came from lightning on Jupiter, and it might be an elf or sprite, but rather elf, because elves are known to produce UV radiation if seen from terrestrial orbit. And these figures show some optical measurements made by Stellar Reference Unit on board Juno. This is the Aurora. Here is lightning. Here are several lightning detected a few milliseconds apart. And this is the measurement of Hubble telescope showing the convective clouds and the detections by wave instruments on board Juno. So we are quite now close to the conclusion that lightning on Jupiter are very similar to what we have on the Earth. So Venus, this is quite controversial because there are quite a lot of missions which were orbiting or even landing on Venus, but the results are inconclusive. So from these gray ones, it came out that there are no lightning on Venus from these two missions, which detected signals which look like that. The authors of the paper assumed that it might be lightning whistles on Venus as an evidence of lightning on Venus, but the community of atmospheric electricity doesn't believe it. Yeah, so this is quite inconclusive. We are waiting for the other missions coming to Venus to show if there is lightning or not. Akatsuki has an optical instrument orbiting Venus from 2015, no detection. But it may be because the clouds from the sulfuric acid are too opaque to see lightning in optical range, but the clouds are not a problem for electromagnetic signals, so we still don't know. And what about Mars? We know that on Mars there are plumes of dust which could be 20 kilometers long, and in such columns of dust are happening volcanic lightning on the Earth. So based on its analogy with volcanic lightning, it was also found in laboratory experiments that in the mixture of Martian soil particles, lightning were initiated, were numerically simulated. There are also emissions of non-thermal microwave radiation by Mars dust storm, hesitating if there are Schumann resonances on Mars, but up to now, we do not have a clear evidence of lightning on Mars. And we built an instrument for the ExoMars rover. It's this electric antenna and this magnetic search coil, like you have seen on Magion and on the other spacecraft Andre was showing. But unfortunately, the mission was canceled due to the war, and this antenna is still sitting somewhere in Torino, and we are not able to find if there is lightning on Mars by direct measurement from the Mars surface. So here is my summary. Lightning is a powerful natural discharge. There are 50 to 100 lightning discharges at the same time worldwide. The spatial and temporal scales of lightning vary by 10 orders of magnitude. There are transient luminous events dancing about the thunderclouds. Thunderclouds produce amazing amount of gamma rays as the gamma glows and terrestrial gamma ray flashes. Lightning discharges were found on all gas giant planets. Lightning-related signals can be observed at large distances from causative strokes. It depends on the frequency. In case of Schumann resonances, the signals can travel around the whole globe. In case of VLF measurement, I mean, tens of kilohertz can travel several thousand of kilometers. And now it seems that we need a multi-instrument approach to investigate the lightning from all sides, all perspectives. And this is my part, and after the break, you will have a task, and I will introduce you what you can do at large scale, and at small scale, you can select simply one topic or do it as a homework. You will see. Thank you. lightning, I have selected two tasks. One is related to the electrified Hurricane Harvey, which I showed you before. And the other one are electromagnetic signals detected by our antennas. We distributed at 7 places in Europe. And if you are lucky, you can identify lightning pulses there. So as regards the large-scale task, you might be able to download from the Google Drive the data where there is a hurricane track, which is provided by NOAA. This is the position of the Hurricane A in a 30 minutes period. And lightning data from the whole hurricane movement from 16th of August to, this is not correct, this is 2nd September 2015. These are data from Woolen. This is the Global Lightning Location Network, which provides for every detected stroke the location, time, and energy. Like this. This is the ASCII file, these Woolen data. There is date, time, latitude, longitude. You do not need to take into account this residual fit error. Number of stations which detected, which contributed to the detection, energy and energy error, and number of stations used for the energy estimate. This is the Woolen is lightning location network, which works in the low frequency range. They have 70 stations across the globe. And if the signal is detected by at least 5 stations, it considers the location as reliable. It works in the time of flight method, as I showed you also for these smaller arrays. And the energy is estimated as a radiated energy during 1.3 milliseconds because the signal is composed not only from the ground wave, but also for few sky waves coming from the reflections from the ionosphere. So this is the burst, wave burst, and they calculate the energy integrated in the frequency range from, I think, 5 to 17 kilohertz for 1.3 millisecond, and this is the energy in kilojoules. And the energy error is usually quite huge. And the task would be to try to read this ASCII data, and you might start to plot them simply on the map, how this will be the whole world data. All data from the whole world detected during these days from 16th of August to September 2nd. And the task might be, for example, you can look at the trace of the hurricane and to calculate the distance between the discharge and the hurricane eye, and to select it only the discharges which were occurring up to 2,000 kilometers or 500 kilometers or whatever you select from the hurricane eye. So you might be persuaded that these belong to the hurricane, because if it is more far away, it might be simply convective clouds which are occurring with any connection to the hurricane. So if you look at the ASCII files, there is one file for day, organized by time, and you can start to plot them on a map. Here I color-coded it by time, so what happens at the beginning of the hurricane movement is blue, and how it arrives to the continent, it then changed the direction, and the later lightning occurring at the beginning of the hurricane movement are in red. So you can try to play with this lightning detection network data. They usually look very similar. If you have the data from other lightning detection network, instead of energy, you can have peak current in case of these more local lightning detection network as Euclid, which is the European one, or an NLDN in the US, or a Canadian one. There is also one in Italy. So then they provide usually the peak current instead of energy, and they also, based on the wave shape of the pulse, try to estimate if it was cloud-to-ground discharge or intra-cloud discharge. Here we do not have any idea if it is cloud-to-ground or intra-cloud. It simply is a pulse which the Woolen network detected. And so try to play with this and plot it on the map. And if you are able to plot it in the map, you can select only these which might belong to the hurricane. And here is another plot showing the Woolen energy across the time when the hurricane, these 400 hours when it was moving in the Atlantic Ocean. And these error bars are coming from the energy error. And the number of lightning is increasing, and it was different at the different stages of the hurricane. This was the most intense part, and this was also quite intense part. So you might also plot the energy of lightning if you select these which belong to the hurricane. It's pretty average. 1 kilojoule is pretty average Woolen lightning strokes. So this is one possible task, and the other one, I will introduce it just now, and then you can select. Here I'm also showing that you can plot it into 2D histogram as a distance from the eye in the north-south and east-west direction, and you can see that there are these rain bands which were more rich on lightning. So it's up to you how you will play with this data set. And as regards the small scale, these are waveforms which show the lightning stroke from its initiation up to the return stroke and some post-return stroke processes. So this is quite typical return stroke. These are negative cloud-to-ground lightning, quite strong ones. These are initial breakdown pulses, which are shown here or here. These are regular bipolar pulses, quite typical. You can identify the lightning initiation based on these pulses. So what you can do here, for example, you can identify the peaks and then look how the evolution of intra-pulse duration is changing, or how the amplitude is changing to simply have the shape of that burst of pulses. And for this initiation pulses, you might download the binary file which comes from our antennas. This is the antenna which we have in southern France, approximately 70 kilometers from Marseille. This is the simple magnetic loop antenna. This is made from sewage tubes, and in the middle of it there is a wire which makes one loop. Here in this place there is a preamplifier, and it simply detects the fluctuation of the magnetic flux coming through that surface, and at the output there is voltage which is digitized, and this loop doesn't measure the magnetic fluctuations of the magnetic field directly. It measures the time derivative of the magnetic field fluctuations. So to get such plots, you need to read the binary data, which I think is possible to do in any language which you are using. Is the information which are given here. And to integrate the data to have such a nice plot. Then you might try to write a procedure which allows you to select the times and amplitudes of individual pulses. So it's probably more complicated than the hurricane case. And here are even smaller scales. These are pulses which are generated during the propagation of the in-cloud discharge through the cloud, and these are much shorter distances one to another. And here I put 3 examples which were detected by our antennas. These are antennas which are placed at our observatory, which belongs to our institute at the Milešovka mountain in the northern Bohemia. And the system is the same, simply you need to read the binary data. These are two bytes samples, and one to one, following one after another. The time, similarly as in Ondřej's case, is derived from the sampling frequency. It means every 5 nanoseconds it's a new sample. And again, you need to integrate the waveform to have this magnetic field data. So this is all. I can help you with it. What you want to. I can go back with the hurricane if you would like to start rather with the hurricane, or if you would like to start with the binary data, you can look at the presentation. There is a description. I uploaded the presentation as well. So it's up to you what you would like to start with. So this is simpler, more simpler, because this is ASCII file, easy to read. And you might need to find the equation with which you can calculate the distance between 2 places on the globe, where you have the longitude and latitude of one place and longitude and latitude of the other place. You need to calculate the distance between them, if you would like to produce a plot which is similar like that. But you can simply start with the plotting the discharges on the map.